In this video, we are going to learn about attractive forces. Attractive forces are forces that are going to be present within and in between molecules. If these attractive forces are going to happen specifically within the molecule, within the bonds of the molecule, then that is defined as an intramolecular force. On the other hand, if we're looking at forces that are going to happen in between molecules, then those are known as intermolecular forces. When it comes to intramolecular forces, we only have two types of forces, either ionic bonds or covalent bonds. Out of the two, ionic bonds are going to be stronger. When it comes to intermolecular forces, we have four types, either ion-dipole interactions, hydrogen bonds, dipole-dipole attractions, or London dispersion forces. Notice that there's different strengths, specifically when it comes to intermolecular forces. The weakest out of the forces is going to be the London dispersion forces. And as we move up, these forces are going to get stronger, meaning that an ion-dipole interaction is going to be stronger than hydrogen bonding. Hydrogen bonding is stronger than dipole-dipole, and dipole-dipole is actually stronger than London dispersion forces. Let's look at each of the intermolecular forces individually to better understand them. First, let's look at ion-dipole interactions. Ion-dipole interaction is going to be an attraction between a charged ion, it could be a cation or an anion, and a polar molecule. In figure 5.12, we have the interaction or the illustration of the force between the sodium cation or the chloride ion with water. To illustrate the water, I'm going to write in, at least for one of the molecules, the atoms in water. The red dot is going to represent the oxygen. The white is going to represent the hydrogens. We recently observed how water is a polar molecule, and let me just draw it on the side. Because when we look at the electronegativity difference between oxygen and hydrogen, that hydrogen is electropositive, so partial positive. Oxygen is more electronegative, so we assign a delta negative. So when we have an ion-dipole interaction, in this case, our polar molecule is going to be water. And when we look specifically at the cation, we can observe that that ion-dipole interaction or force is going to be a dotted line. Then we draw between the delta negative portion of our water to the cation. In the case of an anion interacting with a molecule that is polar, then the anion, and let me just put in the atoms in the water. This is oxygen, this is hydrogen, this is hydrogen. The anion is going to interact via dotted lines with the partial positive in the water, which happens to be hydrogen. Remember that when it comes to these interactions, these are not bonds. Since they're interactions, they're usually illustrated by dotted lines. Let's now observe hydrogen bonding. Hydrogen bonding is present in polar molecules that specifically are going to have to meet two parameters. Number one, a hydrogen atom needs to be bonded to what is called a fun element. Fun comes from the idea that F is for fluorine, O is for oxygen, N is for nitrogen. So in your molecule, you need to have hydrogen bonded to either fluorine, nitrogen, or oxygen. Additionally, the only way that we can have hydrogen bonding is that the other molecule also contains fluorine, nitrogen, or oxygen as an atom. Let's look at an example of a molecule that has hydrogen bonding by looking at water interacting with itself. When we look at water interacting with itself, I'm focusing on the image that we have on the left side of the slide in figure 5.13, where we can observe that dotted lines are illustrating the hydrogen bonding. In water, this hydrogen bonding event is going to happen between a hydrogen atom with the electronegative oxygen in the neighboring water molecule. Essentially, when it comes to this, you need a polar molecule. And since water is polar, it's going to happen. But the parameter of specifically having a hydrogen bonded to fluorine, oxygen, or nitrogen must also be met. And we can see that water, since it has hydrogen connected to oxygen, hydrogen bonding explains the interaction that happens between those water molecules. Next, let's look at dipole-dipole interactions. Dipole-dipole interactions also happen in polar molecules. In dipole-dipole interactions, this is an attractive force that exists between two molecules that have a polar bond that specifically is going to be permanent, meaning the bond polarization in the molecule is there at all times. Now, the difference between dipole-dipole and hydrogen bonding is just that even though they both require polar molecules, remember that in hydrogen bonding, you must have a hydrogen connected to fluorine, oxygen, or nitrogen. And in dipole-dipole, you just need a polar covalent bond or the molecule to be polar. So let's look at the example of HCl. In HCl, this is a molecule that is polar because the electronegative distribution between hydrogen and chlorine is greater than or it is in between 0.4 and 1.8. So this is a polar molecule, and how we illustrate the dipole-dipole interaction, even though they're not included here, this pink area illustrates that this dipole-dipole interaction or attractive force comes from the idea that the interaction is between the partial negative in one molecule to the partial positive in the next. So you can imagine dotted lines between the chlorine of the one molecule to the hydrogen of the neighbor. Lastly, we have London dispersion forces. London dispersion forces are very weak attractive forces that actually exist in all molecules. Is just that specifically for non-polar molecules, this is their strongest attractive force. As long as a molecule has electrons, they're going to have London dispersion forces. But in non-polar molecules, that's the only force that is going to exist. What happens in London dispersion forces is that specifically we are going to have non-polar molecules that are going for a moment to develop a temporary dipole. This temporary dipole results from the electrons circling around the nucleus of the atom, And then for a moment, it's going to create a temporary dipole because the electrons are going to populate one side of the molecule. So in letter B, we can see how the electrons sit mostly on the left side of the atom. So this means that the nucleus, which is where the protons are going to be pushed towards the right of the molecule. And this creates, for a moment, a dipole. Now, what happens is that once one atom creates that dipole, it induces dipoles in the neighboring molecules. So we can see in letter C that atom B induced a dipole on atom A. Understand that these London dispersion forces, once the electrons keep on circling, they return back to their original state. So that's why these are known as temporary dipoles, because they're not permanent. The only molecules that have permanent dipoles is going to be polar molecules. So using the idea of specifically looking at the polarity of the molecule, that can give us an insight into the strongest intermolecular force in a substance. In the example that we have on slide 21, we are looking at the Lewis structures for different molecules. Let's first target letter A. We have specifically nitrogen triiodide. When we look at nitrogen triiodide, and when we're doing these type of examples, the first thing that you need to determine is the polarity of the molecule. Looking at the Lewis structure for nitrogen triiodide, I can observe that this molecule is tetrahedral because it has 4 electron domains, lone pair, single bond, single bond, single bond. If a tetrahedral molecule is nonpolar, then that nitrogen should have 4 of the same atoms. Since it doesn't, then that means that this molecule is polar. When you have a molecule that is polar, then in essence, when it's interacting with itself, then it means that our options are going to be either hydrogen bonding or dipole-dipole attractions. Since this molecule does not have any hydrogens, then the strongest attractive force present is a dipole-dipole attraction. Next, in letter B, we have HF. HF is a linear molecule that has a polarized bond. Since the molecule is linear and it has a polarized bond, then that means that this molecule is polar. When you have a polar molecule, basically you're trying to decide what is present in terms of attractive forces, dipole-dipole or hydrogen bonding. Since we observed that in this molecule, we have a hydrogen connected to fluorine, which is one of the parameters for hydrogen bonding, the strongest intermolecular force here is going to be H bonding. Lastly, we have in letter C, Br2. When it comes to Br2, we can observe that Br2 is a non-polar molecule because this is a linear molecule that has symmetry. Moreover, this bond does not have polarization because you're comparing a bromine to a bromine. So this is a non-polar molecule. In non-polar molecules, there's only one intermolecular force that explains it, and that is London dispersion forces. Attractive forces have effects on physical properties for molecules. For boiling point and for melting point, the strength of the attractive force basically define that if you're comparing two molecules, the one that has a higher attractive force will tend to have higher boiling and melting points. So what we see in this image, that if we compare dispersion or London dispersion forces to dipole-dipole, to hydrogen bonding, to ion-ion, or ion-dipole will be in between these two. Since strength goes in this direction, then we are going to also see that melting point and boiling point will increase in this direction just by looking specifically at the attractive force present in a molecule.